Tech Heart Homes. We fabricate your dreams as real. Fabricated villas, resorts, residential homes, hotels, QSR outlets, commercial places. We blend most sophisticated technology and art. Do any arms to the nature. At the same time, contribute new petals to the serenity of nature. Fabricated house should last over 100 years. And in this respect, by no means worse off than conventionally built house. We offer completion in 100 days, 25 years of construction warranty, 30% cost reduction, 20% materials are reusable, painting with putty work, UPVC windows, branded wires and other accessories. You can dream, we can make it possible. Tech Heart Homes.
Hello, hope I'm audible. Hello, may I know if I'm audible?
Yes, yes,
Yes,
Sarah,
yes.
you may start.
Okay. No man of science wants merely to know. He acquires knowledge to appease his passion for discovery. He does not discover in order to know. He knows in order to discover. And this is going to be the right platform for it. A warm good evening to all the inquisitive minds out there. It's a pleasure to have you all here for today's webinar on space exploration conducted as a part of NOAA 3.0. Today is day 5 of NOAA 3.0. Our event is sponsored by Club FM and Tickart Homes. NOAA is a collaborative venture featuring space enthusiasts and communities from leading colleges of the state, which include GEC Thrissur, CET Trivandrum, Mar Athanasius College of Engineering Kodamangala, GEC Kannur, GEC Idiki, NSS Palakkad, RIT Kottayam, TKM Kollam, Amrita School of Engineering, Amritapuram. The initiative focuses on promoting space research and exploration as a bright career option and promises to offer unparalleled opportunity to learn from industry experts, network with peers, and explore the latest developments in space technology. Now, I invite the speaker and guest of today's session, Sri Alvin P. James, a science communicator and an aspiring researcher. He did his master's in physics from NIT Calicut. Sir would help us gain insights on the so-called complicated computational cosmology. Now, I hand over the session to Sri Alvin. Sir, please.
Thank you, Sarah. I hope I'm audible. And can I know, are there any non-Mallus here? Like, do I need to shift to, can I shift to Malayalam, or there are any non-Mallus? You could just raise your hands or something. Yeah, there are. So, yeah, it's fine. It's fine. Yeah. I see you guys. Okay. And I do want this to be an interactive session. So, if there's anything which you find which is troubling in between, do let me know. And if I'm not audible in between, do let me know. And if that's all fine, I'll start. Like whenever I say something, if it's not clear, just let me know. I don't want to continue without you guys understanding what I'm communicating to you. Okay, fine. So as a title suggests, what I want to convey is to give you a brief understanding on what is computational cosmology. Basically, what we do in computational cosmology, as the title suggests, like basically we try to bring in the universe in a box. And I know that doesn't make any sense. And what is much more easy would be for me to show you a picture of, let's say, even if I'm speaking to you about a tiger, or let's say even an elephant, it would be much better and much more practical to show you what it looks like than to tell you, okay, it has a very big legs or it has a very long trunk or all those things. But that doesn't make any sense to you without the big picture. But the question is, if I am to show you a picture depicting computational cosmology, do I have such a picture to show you what cosmology? If I, let's see, if I say I'm going to talk about sun, I could show you, okay, this is sun. But if I'm going to talk about, let's say, the moon, I could show you this is the moon. I could take a picture of those and show it to you. But when it comes to computational cosmology, there aren't any pictures available. So what do we do when we do not have something? We try to make something. And these days, it is much easier and easily accessible for us to make pictures. You just need to give it a prompt in an AI, and I've generated these images using the photo AI. Basically, I just gave something like computational cosmology, intro to computational cosmology, and these are some of the images the photo AI gave me. But as you can see, not even any of those pictures gives you any idea about what computational cosmology is. I mean, I don't understand what these pictures mean. I think AI has a very good imagination, and it just gave me something which is very vague or something. So even after trying to give an idea regarding computational cosmology using a picture, seems not that fruitful. So we'll try to tackle the concept of computational cosmology part by part. First, let us understand what cosmology is. Then we will move into what computational cosmology is. I think most of you are readily familiar with these two terms, which is astronomy and astrophysics. And we do these days use these terms interchangeably, but there is a very proper definition on what these are. Astronomy is basically, let's say, at night, you all go out, you all look at the skies. And if you try to understand the different positions, where moon is, where Mars is, let's say where Venus is, then you are successfully become an astronomer. And if you start asking the question of how the moon came to be, or more like what is moon, or how our sun glows, all those physical questions, you become an astrophysicist. So that is the proper, when you take the terms for granted, or when you take the terms for its definition, that is how astronomy and astrophysics are differentiated. But these days, you can see that these two terms are used interchangeably. And astronomy these days means astrophysics, and astrophysics these days means astronomy. Because time has come where these people who look at the stars do try to understand what those stars are made of. And these days, most of the astronomers there are still amateur astronomers, but the line between astronomy and astrophysics have blurred completely in this new era of astronomy and astrophysics. So the question still remains, how is our cosmology related to these terms? These terms, as we know, are very familiar. I hope all of you are familiar with these two terms. That is where these two questions come into play. Let's say you're taking a shower and you start pondering about these questions. How did the universe come to be? How it evolves? Or let's say, will it end? We're all part of a big universe. And we're not just speaking about the solar system as a whole, we're speaking about all the stars, all the galaxies in it. And we can ponder these questions. How the universe is formed, how it evolves, and how it is going to end. There is an end. Hopefully there will be an end. And that is where cosmology comes into play. If you get a more proper definition of it, we can say cosmology, the scientific study of large-scale properties of the universe as a whole. You try to understand, in cosmology, our smallest building block, or let's say when you say it's atom when it comes to matter and all, when it comes to cosmology, our smallest building block is the galaxies. When it comes to for a cosmologist, he doesn't care what galaxies are made of. For him, galaxies are the smallest fundamental parts. And we try to understand how these galaxies are distributed, how these galaxies came to be, how these galaxies evolve, and all those things. So we understood in a more general scientific perspective what the term cosmology or what the study of cosmology deals with. Now, as I said, we try to understand the universe as a whole. Before that, we need to understand where we are in the universe. If they ask you to write an address, you would, let's say, many of you would be in, most of you in Kerala, you will write, okay, my home, my house name, your street name, your district, your state. Then you would say country, India, then you say continent, then Earth. And where is Earth? Earth, we would say, is a planet in the solar system. Solar system is a stellar system in the Milky Way galaxy. And the Milky Way galaxy is basically a group of galaxies called the local group. And these local groups and other groups together form something called the Virgo supercluster. And this Virgo supercluster and other superclusters together form something called the Laniakea supercluster. And together, it's all in the observable universe. So when we say Earth, we're just an average planet in an average star, average planet rotating around an average star in the outskirts of the Milky Way. And I'm sure there would be some life somewhere in another planets or another stars. There are billions of stars, and the stars you see are just from the Milky Way galaxy. There are the millions and billions of galaxies out there. So I told you how the questions which we deal as a cosmologist are the questions of how universe is formed. And the scientists right now are in a consensus that the most accepted theory of the evolution of the universe, or how the universe formed, is something called the lambda-CDM model of cosmology. So what is the lambda-CDM model? This lambda-CDM model basically says that the universe is created by a big bang, and then there was something called inflation, recombination, dark ages. It's after these three stages that the first stars and galaxies form. Then if you take the current distribution of the galaxy, we have something called 5% of the ordinary matter, 27% of dark matter, and 60% of dark energy. I don't want you to dwell into this. We'll look into each of these terms in detail in the coming slides. But I do want you to understand, when you speak about cosmology, when you speak about Big Bang, this is how we believe, or how the general scientific community believe, the universe as we see today as formed. Started with something called the Big Bang, inflation, recombination, dark ages. It's only after those dark ages we see the first stars forming. Then currently we see a universe of this particular distribution of matter. And how? Like basically you can't just bring in the idea of the Big Bang model, or you cannot bring in the idea of all these lambda-CDM model of cosmology just from thin air. You need to have theoretical basis on which these models are built. So when you speak about the foundations of cosmology, it's basically between two things. One is a general relativity. It's basically a very advanced theory of gravity developed by Einstein, and it is very hard, and I wouldn't want to mince my words. It's really that hard. And basically you study mathematics more than physics when you deal with GT as a course. If you take this in the university, you would study let's say quarter, like half of your semester would be studying tensors and all. We basically use mathematical tensors to depict the universe, and we put in some other tensors to depict mass and all, and we tell the universe as a whole, or the space as a whole, curves based on this particular theory. That is what general relativity. This is one of the foundations of the Big Bang model, or let's say the lambda-CDM model. The other foundation is basically the cosmological principle. So if you take in a very local space, let's say in Earth, if you look towards the sun or looks towards the star, you could say that it is not same. You could see different stars in different places. The cosmological principle says that whichever point you take in space or whichever direction you look in space, it's just the same. The cosmological principle has two ideas. One is the homogeneity of space and the isotropy of space. Even if you are standing anywhere in space, it doesn't matter. Even if you are looking any directions around you, it shouldn't matter. But this cosmological principle comes into play only in a very large scale. Let's say 200 megaparsec. I don't want you to dwell into those terms or those numbers. I want you to understand when we speak about the cosmological principle, we're speaking about very large scales. Yes, it is not homogeneous in a very short scale. Like you wouldn't see an equal distribution of planets around the sun. You cannot see equal number of planets if you look right or left from Earth. There is disparity. It is not homogeneously distributed. There is no isotropy. But when you look in a very extragalactic scales or in a cluster scales, you could find this homogeneity and isotropy in the universe. So the idea of cosmology or the idea of lambda stadium model is based on these two theoretical pillars. And this is how you depict the Big Bang model. Basically, I hope you can see my cursor also. At this point, there was something. See, basically, we have never seen Big Bang. Okay, what we see to the maximum, how much large is needed? Varghese, I didn't get your question, right?
You told large scale is needed to get homogeneous.
And I think at least a minimum of 200 megaparsec needs to be there.
200 megaparsec.
200 megaparsec. Yeah.
Okay.
And so, if you can see this image, basically, this is currently, let's say this is currently where we are, 13.8 billion years into the future after the Big Bang. So I do want to tell you that we have never seen this Big Bang. If you look at the sky, what you see is the past. The sun you see is basically, I think, 7 seconds or like 1 point some minutes old. The light which comes from the moon is a particular seconds old. If you look at the stars, clearly years old. So basically, the farther you look, it's basically you're looking into the past. The night sky is basically a time machine. So if you are here and if you're looking past, you can easily see older and older galaxies, older and older point, and there comes a point where you won't be able to see anything. That's where the dark ages. So why is that? And even if you just look back, basically the maximum background which you can see is something called the cosmic microwave background. It is from there we have extrapolated. Let's say, okay, we see that every object in the sky is going away from each other. So what did the scientists say? If everything is going away from each other, in a point of time in the past, it could all have been at a single point. So that's how the concept of Big Bang comes. When the very distant past, that is 13.8 billion years ago, everything which you see were at a single point. And there was a big bang of some sort and it all just scattered from there. So here you can see this Big Bang. And there was a sudden inflation. Inflation is basically a sudden expansion. I want you to think of inflation as a sudden expansion. And then the first 3 minutes, there were a lot of things happen. First protons formed, then nuclear fusion begins. Then nuclear fusion ends because the nuclear fusion which happens there is for a very small scale. Let's say hydrogen, helium. I think lithium is also formed. You cannot form this large iron or all those large atoms in this initial nuclear fusion phase. Nuclear fusion is basically two atoms coming to form a new atom. You have two hydrogen atoms. If you merge those together, you get something called the helium atom. Similarly, after the first protons were formed, protons together formed into some helium, some protons formed into lithium. And the thing is, the universe at this time was very hot, and there was no light. Basically, there was no place for this light to pass on because it's all like hot, dense gas. And the point where the first light was emitted is what we call the cosmic microwave background. It was emitted, let's say, some in a very high frequency wavelength or a very high energetic light. We could say maybe some gamma rays or X rays or something. But at the moment, it has been red shifted. What happens is that when light pass through the universe is expanding. So if it is a X-ray, when it comes to us, the wavelength has been extended so that it has become a microwave right now. So if you look at the sky, and if you have the old TVs with that static, that grains used to come when you don't have a channel or source, that is what the microwave background is. So microwave background is the first light. So after the first light, you wouldn't have any light. So basically you have some atoms there, but you do not have any stars to form new light. So until the first stars form, what you have are the dark ages. So there are no light. There aren't any new light. So if you look at the sky before the first stars, you would find a period in between where you cannot see anything. So what we see at night, if you look up, why is that the CMB maintained it's a black body? Okay, fine. So yeah, CMB is basically a black body spectrum of I think 2.7 Kelvin or something. And if you emit, let's say this cosmic microwave background has emitted a black body of a higher temperature. When it is redshifted, all the waves are redshifted. It is not that only some of the light that comes are redshifted. Whatever radiation has been emitted at that time has been equally redshifted when we observe it. So that is why even if the black body peaks at some point, whatever the curve is, all those points, all those light have been equally redshifted. That is why we see that. And I'll come into that, why or cosmic microwave background is relevant when we move forward. So we are under the assumption, you're fine. We are under the assumption that the universe is homogeneous isotopic, right? I did mention that cosmology is based on those fundamental idea of homogeneity and isotopy. So after this dark ages, we have the stars. Then after some stars explode, then they form again, they form new stars. That's how the cycle continues. And right now, 13.8 billion years after, we are there at the current time. As I said, if you look at the universe right now, what you see is basically 5% of ordinary matter. And these 5% ordinary matter is basically the matter which we see around us. Matter in hot intergalactic gas, warm intergalactic gas, cool intergalactic gas. And all the matter which you can see, if I would put it into the so-called ordinary matter. Then we have something called the dark energy. So basically, dark energy is not as elusive as you see in all those sci-fi series and sci-fi movies and all. What we know about dark energy is basically from Einstein's theory of relativity. When you look into Einstein, energy and mass are basically the same thing. So when I say universe as a whole, 100% divided into 5% ordinary matter, 25% dark matter, 70% dark matter, this is the energy matter content. So basically both energy and matter are taken into account when you say these percentages. So if you look at the general theory of relativity, you need to have a universe which shouldn't be accelerating at the rate it is right now. So basically there is some gravity as the idea, gravity as the force of, let's say, it pulls everything closer, gravity. But what we see is that rather than pulling everything closer, there is a acceleration. Everything is moving apart at an accelerated rate. And we could not explain that using the general theory of relativity. That is where dark energy comes into play. We use dark energy to explain those unaccounted energy with which the universe is expanding. Temperature or radiation. If I'm right, I think it's the radiation temperature. I'm not sure about it. Basically, it's 2.7 Kelvin plus or minus point something is the temperature of the cosmic microwave background. Those small changes is basically the small perturbations. And I will go into those perturbations because those small changes from 2.7 Kelvin are very important when we move past all this. Okay, so basically what we know about dark energy is basically there is something which we cannot account for in this cosmic expansion and we call it dark energy, and that is it. Whatever you see in those sci-fi series, there aren't any scientific basis to it. They're just conjectures. Maybe there are even scientific ideas or hypotheses, but what we know for sure is that there is something missing and we call it dark energy. That is it. Similarly, it goes for dark matter also. Basically, what we did was that if this is the center of the Milky Way, this is the Milky Way galactic curve, and we measured the velocity of different stars up to this point. This is the sun's speed. And after that, we basically use something called H1 alpha. I think we use H1 emissions from hydrogen there. Basically, what we do is that we try to measure the velocity from the center of the Milky Way to the outskirts of the Milky Way. Velocity of with the objects are moving around the Milky Way. You do know that Earth is rotating around the sun, and sun is not a stationary object. Sun is rotating around the center of the Milky Way. So if that is the case, what we know from the Newtonian Kepler theory and all, the curve should have gone like this. If you look at the Mars, which you can see, this is a predicted curve. But what you see is something like this. There is a disparity. This disparity is basically what we call dark matter. Other than this, we do not know anything. I do stress this point. When you see these sci-fi shows and all, you come up with a lot of new things where they say dark matter is that, dark energy is this. But these are the only things which we know for sure. There are some unaccounted mass, and we do not know what that mass is, and we just call it dark matter. There is something which interacts gravitationally as if there is as if it has mass, but we cannot see. It's like if you take a weighing machine and suddenly there is a 10 kilo there, and if I take a, let's say, if I weigh this and if I look at it, I see it to have a 10 kilogram of mass if I look at it, but when I weigh it, I see 100 kilogram mass. There's nearly 90 kilogram of mass missing. So that is what dark matter is. We do not know what that is. We just call it dark matter because we see some mass there and we do not see it in that. So that is fundamentally that is only what depends on the dark energy. So if I remember correctly, dark energy estimation is basically done using type 1a supernova expansions. So what we do is that we have data of type 1. Okay, we need to understand how the universe is expanding, right? So it is not easy to understand how fast the galaxies are moving away from us. So basically, there is something called type 1a supernova. Supernova is basically explosion of a star, and these galaxies, distant galaxies, we look for these type 1a supernovas, and we estimate how fast these galaxies are going away from us. And we have the Einstein's equation, something called the Friedmann equation. In a very brief way, I'll explain that. I told you, like, Einstein's general relativity and the homogeneity and isotropy forms the basis of cosmology. So basically what you do is that you take this idea of homogeneity and isotropy, you take general relativity, and you put this homogeneity and isotropy into the Einstein's equations. And you get something called the Friedmann's equation. And this Friedmann's equations govern all this. So what you do is that we put in this expansion rate into this Friedmann equation, and we see it is not matching up. And those amount which is not matching up, we call it dark energy. That is how we get this percentage. I think it's fine. Okay. So currently, right now, I spoke about what cosmologies, or more thoroughly, what cosmology deals with. Then we spoke about the current idea or current model of cosmology, which most of the scientific community believes in. Now, I said basically there's something called dark matter. If you take a galaxy, and if you take a Milky Way, all these galaxies are engulfed in something called the dark matter halo. So whatever galaxies you take, it all has a dark matter halo surrounding it. And it is said that most of the galaxies can only be formed in the potential wells, or let's say in more simple terms, let's say we have a lot of dark matter, and these dark matters comes together because of gravity and form something like a globe or something. Exactly. Basically, this dark energy or dark matter is basically just to match the equations. That is what we do. There is something we cannot match the equations with the observation. We observe something and we try to explain this observation with the equation. And whenever we see that, okay, the observation is not matching with the equation, you put in new things. That is what that is basically what dark matter. That is basically dark energy. There's nothing more. We believe our theory or our idea of the gravity is right. And so as to make our theory of gravity right, whenever we find discrepancies between the observation and the theory, we will put in new things and we call it dark matter and dark energy. That is fundamentally it. Yeah, I know you all find it skeptic, but that's what cosmology does. So what I'm trying to say is that we have dark matter particles, and we believe we only interact with gravity. So these dark matter particles clump together to form. For that, basically it's not about statistical significance. It's more about, let's say, when we speak about this galaxy rotation curves, we do know that at, let's say, 35 kiloparsecs, we do know that the velocity which we observe there is of the order of 200 kilometers per second. But if you look at the mass, you can only find the velocity. If you look at the mass and calculate using that mass, you would only see a velocity. You should only see a velocity of 100 kilometers per second. There is a difference of nearly 100 kilometers per second. So whatever that difference, you add an extra mass, so that that difference is made up. That difference is tallied out. So that is how these comes into play. I think that's clear. So what I was speaking about is that we have these dark matter particles which only interact with gravity. They clump together to form dark matter halos. And what we believe is that in these dark matter halos, which only interact gravity, these galaxies form. So in this dark matter halos, let's say we have some visible matter, and this visible matter, let's say some protons and all, these go into this dark matter halos, and inside this dark matter halo, we get the formation of galaxies at all. So I did say that the idea of cosmology, we believe the universe is homogeneous and isotropic. If we have a universe which is homogeneous and isotropic, how do the structures form? As I said, if you look around us, you can see galaxies, you can see all sort of inhomogeneous structures. Galaxies, planets, stars, and all those things. But our fundamental idea when it comes to cosmology is the idea of an homogeneous universe. So to tackle these questions, we bring in something called perturbations. Remember the cosmic microwave background? I told you, if it was a very well distributed, it should all have been 2.7 Kelvin. But you can find small changes or small discrepancies between the temperatures at different points in this cosmic microwave background. And it's an order of, let's say, 10 plus or minus point something Kelvin. That small changes are the perturbations. We believe these perturbations are due to quantum fluctuations during the inflation. So basically, some Big Bang happened. During that time, there are some quantum fluctuations, and these quantum fluctuations evolved. Initially, they evolved for something called the baryonic acoustic oscillations. I don't want to delve into that. Basically, in a very homogeneous and isotropic universe, there were small changes in the homogeneity that grew into what we call the galaxies and all those. Yeah, basically, see, it's only 0.0013 Kelvin. It's a very small difference. Those small differences or those small perturbations is what we see as galaxies and other large scale structures here. So we do have equations to these problems, but how do we? It's called the perturbation equations, cosmological perturbation equations and all. The problem is it's not easy for us to solve these equations. So we came up with the idea of cosmology. We came up with an idea of cosmological model of cosmology. We came up with the idea of how we can incorporate inhomogeneous bodies into this model. And we say, okay, this galaxies and all are formed due to perturbations. And we make equations to define these perturbations. Then we come to the next big problem, that is we are not able to solve these equations. We can only solve these equations for very tiny density differences. Density differences in the sense, I told you it is very homogeneous and it is very small changes would come in density. For small changes we can, but and that too for the highly symmetric cases, are we able to solve these equations? So what do we do when we're not able to solve these equations? That is where computational cosmology comes into play. So scientists have made some equations and we're not able to solve it, and we find a new method to deal with it, and that is computational cosmology. In a more genuine sense, it is the modeling of the structure formation in the universe by means of numerical simulations. I'll get into this very easily. So basically, this cosmological simulations, we only deal with dark matter particles. Remember, I told you, dark matter particles clump together to form dark matter halos, and most of the galaxies which we see are inside these dark matter halos. If you take a normal matter, they interact not just with gravity, they interact with, let's say, electromagnetic forces. There is strong interaction, there is weak interaction. But when you take dark matter particles, they only interact with gravity. So when you are to do simulations, you only need to take into account the gravity between these particles. So imagine all these chairs are, imagine this was an offline setup and you're all sitting in front of me in a big hall, and we were randomly in a very homogeneous, isotropically distributed in the classroom. And when it comes to these simulations, we devise these homogeneous initial conditions from the cosmic microwave background and all. And what happens is that, let's say this guy starts forming groups, and he will ask this guy to be part of his group. He will ask this guy to be part of the group. He will ask this guy to be part of his group. And these process of asking the nearby students or nearby person sitting near him is what we call gravity. So basically, what happens is that we run the simulation, and when the gravity, we try to understand how the gravity acts between each particles. They start, when the time progresses, they start to clump together. So we have a lot of different things, and they're clumped together, and we see many clumps of dark matter particles. So how do we understand what all clumps are there? There is something called halo finding algorithms. So these steps are purely computational. Basically, you take a computer, you write a code, and you put in the memory some particles, and you predefine where the particles are. Then you say these particles have so and so mass. Then you put in the equations of gravity explaining how these particles interact with mass, and you forward it in time, and they start clumping together. And then you need to understand which are you need to. It's a computer simulation, so you can't just see and look. So you put in codes to understand where all are these clumps of dark matter, and you run those algorithms and we clump them together, and we call these dark matter halos. So what we did here is, in a computer, we have simulated dark matter particles coming together to form dark matter halos. We have set up the initial condition, we compute the force between the particles, we move the particles step by step based on the force, based on the gravitational force. Then we repeat this second and third step until the time which we need, and we run halo finding. To find these halos, we have many halo finding algorithms. It's something called friends of friends, spherical over density, COMB-ISO, DENMAX, bound density maxima. So basically algorithms or computer codes to understand which all particles are together. That's all, nothing more. Then there are many cosmological simulations, like Abacus Summit is a 2021, one of the latest simulations, and I work using Abacus Summit simulation data. Something like the Quitonde simulation in 2020, Abacus Cosmos in 2018. Basically, you cannot do these simulations in a normal computer. You need to have a supercomputer to do this simulation. Basically, many people have run different codes in different supercomputers, and they've saved the output of the data, and we call those are the different simulations. So until now, we understood what cosmology is. We understood how, or at least I think you understand how in a homogeneous and isotropic cosmology, we can form structures. And we finally saw how, because we're not able to solve these equations of perturbations, we are able to simulate simulate the formation, or let's say to simulate the process so as to see the formation of structures. Why do we do this? And how do we know we are right? Let's say we are simulating this. Let's say we are simulating this for a. Let's say we are simulating this for a cubical box. Our universe is not cubical. And let's say in the computer we are simulating it for a, let's say, 100 megaparsec or 2000 megaparsec. Megaparsec is a unit of distance. It's a very large unit of distance. You should Google it if you want to know more. And we have simulated and we have made these dark matter halos in a box in a computer. How are we to compare this with the universe? So what do we do? Let's say I have two classes. I have 10A and 10B, two divisions of a class. And I want to compare whether class A is performing well in exam compared to class B. We never compare the roll number 1 to roll number 2 or roll number 2 to roll number 3. There may be only 10 students in class A and 50 students in class B. What do? You come up with statistics. Maybe you would find some average mark, or you would say some mean, all those things. Similarly, we come up with something called the statistical properties of dark matter halos. So from these simulations, we define something called the halo mass function and the counting cell simulations, counting cell distribution. These are in simple terms basically like a density, and the other one is basically counting the numbers. I'll briefly dwell into what these are. These are the things I'm working on currently. Currently, which is a thing which I did work during my master's thesis, and which I'm currently working on. So what I did is basically I've taken the Abacus Summit simulation. Basically, it's a highly accurate cosmological simulation. It's run in the Abacus Summit supercomputer in some place in Oak Ridge National Laboratory. And there they use something called the Friends of Friends and spherical over density algorithms child. We call the COMB-ISO algorithm to find the dark matter halos. So I don't want you to dwell much into this equation. I want you to understand halo mass function as the number of dark matter halos divided by the volume. And what we do is that we bin them. Let's say 0 to 10 mass. how many dark matter halos are there? We put in one bin. Then we count 10 to 20. How many dark matter halos are there? We put in another bin. That number divided by the volume of our simulation into the distance. We have put 10, right? 0 to 10. That 10, that is this delta, the change in that bin. This is basically a density. As per volume. Here is a number density, number per volume. And it's in log and all. That is, when you take it in a more academic perspective, you look in log and all, but you want to understand what that is. It is basically number density, number per unit volume. It's a 5 dark matter halos per meter cube. That is it. And this is something which we get if we are to compute the halo mass function. It's not relevant. And this is, I just wanted to show what that is. Similarly, there's something called the Counting cells distribution. So what Counting cell distribution does is that I wanted to look around the room which you're sitting. So I hope every one of you are sitting in a cuboidal room. I'm sure none of you have a spherical room or anything. In a cuboidal room, if I am to divide this room into small cuboids, and then to ask the question of how many, and let's say in your cuboidal room, you have a lot of hydrogen balloons floating around all over your room. And I'm going to divide the room into multiple small cuboidal boxes. And I'm going to ask the question of how many cuboids or how many of those cells have 0 hydrogen balloons. I would ask the question of how many of those cells have 10 hydrogen balloons, 100 hydrogen balloons. That is basically what counting cells is. This is the number of halos in a box and the frequency. We have normalized it to make it frequency, but you need to understand what counting cells is. Counting cells is basically that number. That's it. Let's say if you have 100 hydrogen balloons, how many boxes have 100 hydrogen balloons? You just divide it by the total boxes to get this frequency. No, this is not a Poisson distribution. If you can see, I've only shown it for a particular mass bins. I think it is for 1000 mass bin and all. This changes, and it is properly modeled by something called the gravitational quasi-equilibrium distribution. And it is basically derived from some thermodynamic models. You consider these galaxies as something called gases, and you basically there is another distribution by considering these gases and putting in gravitational clustering and all. That is what it fits. In my study, I could see that this changes from Poisson to Gaussian at a lower mass ranges and all. You could see a different distribution. I haven't put that here. Just one of those distributions. You can see that. So this DQED distribution has a specialty that this changes from this Poisson to Gaussian depending on the number of cuboids I increase. So GQED is the most proper distribution. I've seen that this GQED changing from Poisson to Gaussian at times. So what is relevant is not the distribution. What is relevant is how or what counting cells is. So I spoke about 2 of those statistical properties of dark matters. Again, the question remains, how does it really look like? If we are to calculate these from the galaxies which we see around, and I do want to take you to the point that these statistics are calculated from dark matter halo simulations. When we observe, we are not observing dark matter halos, we are observing galaxies. So, but we do have an idea, or we do have the theory of galaxy formation that most of the galaxies are inside a dark matter halo. So similarly, we will be able to find these counting cells distribution from the galaxies. And we can compare the counting cells from observations. And for that, we have some redshift surveys. And I think Euclid, another survey is going to be launched this year by European Space Agency and all. So when we take these redshift surveys, we take in these galaxy data, and we find counting cells using that data, and we compare it with our simulations, and we can understand that our theory is right. This is how we check whether our theory of cosmology is right to the observations. And that is it. We can derive the same statistics in galaxy surveys and we compare, and if they match, we know our theory is right. This is what computational cosmology does. If you want to look into the codes of like, I don't want to mince my words, like it's very hard to do this. Like when you see the output, it is very nice. If you want to look in the code, it's basically a very computational computational problem to be dealt with. When you look at the statistical property code, you can see, look at my GitHub account. If you need to go through the codes and all. And thank you. I think that's it. Any questions? Hello.
Hello, sir.
Yeah.
Hello, sir. Thank you for the talk. I am interested in learning computation simulations, but I don't know what concepts I should start with. I'm a master's student, so what mathematical or coding concepts should I start with to get into this thing?
Yeah. Basically, are you looking to do it preferably in like cosmology itself, or looking? See, these simulations are useful in most of the places. There is something called hydrodynamic simulations. Simulations are useful when it comes to mechanics. So are you looking into, let's say, astrophysics or cosmology in particular, or in general?
Yeah, astrophysics itself, because I was about to get started with a project where I'm trying to simulate a simple black hole kind of thing. And so now how should I go about it in a regular laptop? I don't have access to supercomputer or something.
Yeah, that is another problem. In a regular laptop, there's something called numerical cosmology, a numerical GTR, general relativity. I think when you're simulating these black holes and all, you need to look into that. But what I work on is basically n-body simulations. And if you email me or message me, I'll share you those materials which I have, and those are regarding computational cosmology. Okay, these are not regarding those hydrodynamic simulations, because if you are to simulate the sun, you need something called hydrodynamic simulations, because there is plasmas, all those other things come into play. If you are to simulate some other GTR, there's something called numerical cosmology, numerical GTR, that's some other thing. So you cannot compare all the simulations, and basically it's all solving equations, if you ask me. Yeah, that's it.
Okay, thank you. One more question.
Yeah.
I have seen your profile as you're a very popular science communicator. So how do you start becoming a science communicator? What do you actually, how do you apply or something?
No. Basically, from a very young age, there are a lot of science societies in Kerala. There's Breakthrough Science Society, there's Astro Kerala, there are all those different science societies in Kerala, that is. So I started as a young student in my school days. I used to attend all these sessions. And after my master's, I come to a point where I'm able to take these sessions. I do have a very, very general background in astrophysics and cosmology and general theory of relativity. I've taken courses in all those. And if you're able to communicate to the public these terms in a very simple way, without any jargon, without any mumbo jumbo, you're a science communicator. That's it. And opportunities is basically, I started by taking classes for, after my master's, I started during the World Space Week time for school students. And I took a class session for, I think, an Astro Kerala monthly lecture. Then one of my friends saw the lecture and they invited me to take a class in one of the engineering college. So that's how you grow. Basically, if people sees your talk and they find it interesting, they contact you to take new sessions. That's how you become a science communicator. And this is my first online talk, to be fair. Like, I'm not comfortable in an online session, because if an offline session, I'll be able to see your faces. Like, are you understanding? Do I need to slow down my pace? Do I need to explain it in another way? So that is not there in an online interaction. So basically, that's how you do it. I hope that's clear.
Yeah. Thank you.
Yeah. Homogeneous after the order of 200. It's not megaparsecs, not parsecs, megaparsecs. It's nice fluctuation in the age of the universe is calculated. No, I don't remember how the age of the universe is calculated, but regarding the fluctuations, it is those fluctuations which we see as these galaxies and local group of galaxies and all. And those fluctuations have grown to be smaller than 200 megaparsec scales. Even if I told you like 2.7 Kelvin plus or minus 00, I think Varghese has mentioned it's 0.00013 Kelvin uncertainty. It's very small, and those small universe is very big compared to this 2 megaparsec. So if you go above those 200 megaparsec, you would see a very well distributed structure in any direction you look or any position you take. So if you go inside that 200 megaparsec, you will see small galaxies, clusters, planets, stars and all. It's those small galaxies and clusters that formed from these initial perturbations. That's how it is. Yeah. Are there any other?
Hello, sir.
Yeah.
Sir, I have a question. I don't know if it's a full question or not. How can you actually say that this dark matter is actually a matter? Is it from the statistical analysis or something else?
Basically, as I've shown you, basically what we have measured is the velocity. What we have measured is the velocity. And let's say I'm taking this. And I know if I look at it, it is supposed to have 10 kilogram. I'm taking a weighing machine and weighing this. And when I look at the reading, I see 100 kilogram. So there is a discrepancy of like 90 kilogram. So we think it is 90 kilogram of matter because we are weighing it. Something which has mass is there. Something which interact gravitationally, it is there. So that difference is basically mass or matter. We call it dark matter. That is what dark matter is. Is it clear?
Yeah. Yes, sir.
Just no more questions. We'll wind up. Inshija, should I? Organizers?
I hope anyone has anything to ask.
You can ask me any questions. Like, it's fine, not just cosmology, astrophysics in general. Physics in general, I wouldn't say, but still, I'll be able to answer. If I do know, I'll be able to share what I do know. No questions.
Sir, can you show some books about this?
You want to understand? See, what is your background right now? Master student, right?
No, I'm a BSc third year student.
BSc third year, right?
Yes,
BSc
sir.
physics?
Yes, BSc physics.
Oh, fine. Then there's something called cosmology from Liddell. You need to understand modern cosmology by Liddell, Liddla. And the peculiarity of this book is that it doesn't use VTR to explain the idea of cosmology. If you know +1, +2, Einstein's theory of Einstein, or +1, +2, Newton's theory of gravity, you'll be able to follow this book. And it explains how this cosmology basically explains cosmology. So if you are looking into computational cosmology, first you need to understand cosmology. I would suggest you start with that. My guide, Dr. Charles, started me with that. So I would also suggest this. Any other question? Any general questions regarding astrophysics, cosmology? Completely fine. And even if you can also speak in Malayalam, okay, right? Like session കഴിഞ്ഞ ആർക്കെങ്കിലും general ആയിട്ട് ഇംഗ്ലീഷും കുഴപ്പമില്ല, മലയാളത്തിൽ പറയാം. ഒരു സംശയം ആർക്കും ഇല്ലേ?
With the registration form, we have attached a question
fine,
including
yeah.
asking any doubts. Okay. Can we read out that?
Sure.
Our coordinators will read out some questions. Okay.
Yeah. Hello?
Hello, sir.
Yeah.
Am I audible?
Yeah, sure.
Okay. A question from the forms that we collected is that what is the role of dark matter in evolution of our universe?
Role of dark matter in evolution. Okay. Basically, as I've told you, these galaxies form in these dark matter wells. So when you see the evolution of the universe, this dark matter, dark energy, and all are intertwined. Can't just take one out and say, no. Basically, if you look at it as a whole, this dark matter, I said, this plays a very big role as per our current understanding of this theory and all. As per our current understood model, these galaxies are formed inside a dark matter well. So that is the role these play. And I do want to stress the fact that if someone comes up with a new theory which can explain all these observations without any dark matter or dark energy, then dark matter and dark energy will cease to exist. These dark matter and dark energy are not based on some observation which we see. It's purely based on the fact that we cannot find something and we call it dark matter. There are certain theories, something called MOND, Modified Newtonian Dynamics and all, MOND, trying to explain without dark matter. So I do want you to, some takeaway is that this dark matter and dark energy are basically a theoretical concept or theoretical idea put in such that our equations balance. Baryon asymmetry, in the sense, are you speaking about the dark matter, like antimatter matter asymmetry? That's baryon asymmetry, right? Yeah, it's a matter antimatter asymmetry problem. Oh, so yeah. The fact is, what I think is we do not know for sure. Whether I think there are many theories. I'm not read into that in a very academic perspective. But I do understand is that in the initial universe, there are to be equal amount of antimatter and matter. But if you have to look around, you wouldn't see any antimatter. All the matter around us is formed using regular matter. So the question is why? How did this regular matter came to dominate? And I think it's still a contested question, and I'm not sure regarding any solutions to that. And yeah, that's it. That's not something I'm working on. I'm not sure regarding that. That's it. Any other questions?
Sir, another question is saying that what are the challenges in simulating turbulent astrophysical phenomena?
Yeah, okay. See, as I told you, when it comes to astrophysical phenomena, you need to take into account fluid mechanics and all those other things. We call it hydrodynamic simulations. Those are the simulations which we talk about when you talk about the simulations of sun and all. Those are all very complicated simulations, solving complicated equations. Some would take a supercomputer, and you need to have a very fundamental idea of the working of these equations, these differential equations. You need to know how to solve this in a computer using numerical simulations. And a high level of computational skills also comes into play. You need to take into account the amount of memory you have, the amount of computational power you have. So all those things comes into play when you are looking at it. So those are the challenges. And when you speak about challenges as in data as a whole, new missions, be it the James Webb mission or something like the Euclid mission, would be bringing us terabytes and petabytes of data. It is not possible for a human being to manually access and process those data. You would require highly sophisticated codes to, nowadays I'm sure AI would take some of the burden, but you still need to write a code for the AI. You can't just say AI will do it. You need to write a code for the AI. So nowadays, when it comes to astrophysics, it's basically intermission of a high-level computer science, high-performance computing engineering, and high-level physics. So even if you are a BTech computer science student, you can easily take a master's, like PhD in computational astrophysics and cosmology, because most of the positions I see are asking for students either from a master's physics background or a beta computer science background. Because nowadays it has become a very, what do you say, a part which cannot be taken apart. It has to be the computer science very integral part of astrophysics and cosmology as it is. Ada, are there any other questions?
Okay, sir, I think we can wind up after this question.
Sure.
How do scientists validate simulation results and ensure that they accurately represent a physical reality?
Yeah, I told you, like when it comes to cosmological simulation, from the simulation, we take something called the statistical properties. And similarly, from observations, we compute these statistical properties. And if those statistical properties match, we say our simulation or the theory matches our observation. That is how we compare simulation and observation. And I hope that is it. And feel free to contact me if you have any doubt, email me, message me, doesn't matter. So thank you. You can wind up, right?
Okay, sir. Thank
Hello,
you.
sir.
Yeah.
Before that, I'll be commenting the feedback form in the comment box. Okay, everyone should fill that in order to get your certificate. So make sure to fill it. I will be sharing it in the WhatsApp group too. Okay. Okay, Sarah. Now you may conclude the session.
Okay. Thank you so much, sir. The session was quite beneficial. From the beginning, in fact, starting from the minute facts, you gave us a simplified version of the concept of universe and cosmology, and it was really new to me. You also gave your own experiences, which are quite going to be quite valuable for passionate individuals who wish to pursue research in this field. So thank you, sir. I would like to thank our event coordinators for organizing this session. Just as importantly, I would like to thank the participants of this session. It was wonderful to have you all here. Lastly, let me remind you all about the conclusive day of NOVA 3.0, which is set to be held in person on April 1st at GEC Thrissur. Mark your calendars and join us in person at Thrissur Government Engineering College. Immerse yourself in an unparalleled experience that you won't find anywhere else. With this, we come to an end of the session. Thank you all.
No, I do want to add a footnote to this. I don't want you to jump into cosmology, or I don't want to jump into all this just for the beauty of it. I understand it's very beautiful. I understand it's very fascinating. But when it comes to the nit and grit of all this, when it comes to the academic perspective, it's very challenging. And it is very, I would say, mathematical than more computational perspective. If you take cosmology, if you take astrophysics, very highly mathematical subject. So I do want you to keep in mind. From a very personal experience, I do want to say that also. Yeah, thank you. Bye-bye.
Thank you, sir.
Thank you, sir.
Thanks, sir.